Hi guys and welcome. In this video I'm going to show you how to derive the general solution to the wave equation by using the method of operator factorization. Now this method applies when x and t are free to be any real number. So both x and t go from negative infinity to positive infinity. So usually these conditions aren't always written down. Whenever you see the wave equation written by itself, we assume that x and t are free to be any real number. Anyway, on to the derivation. So the first thing we're going to do is bring both terms to one side. So this becomes second derivative of u with respect to t minus c squared, second derivative of u with respect to x equals 0. Now if you'll notice, this is a difference of squares pattern. So we can factor the operator. So that's what I'm going to do. I'm going to write the left side as an operator acting on u. So this is the second partial derivative with respect to t minus c squared, second partial derivative with respect to x acting on u equals 0. Now, as I said, oh, I'm sorry, this is a, there should be a 2 here. Now, as I said, this operator can be factored, so I'm going to write it like this. First derivative with respect to t plus c, first derivative with respect to x, and then same thing, but minus c, and now acting on u equals 0. Now, it doesn't matter whether you put the minus here or the plus here. You'll still get the same final answer. That's what's most important. If you want, you can redo this derivation on your own, but switching these signs, and you'll see. So the next step is to let this part be v. So that way this equation reduces to first derivative with respect to t plus c, first derivative with respect to x, acting on v equals 0. And this is just partial of v with respect to t plus c, partial of v with respect to x equals 0. So let me summarize what I've done here. By making the substitution, I have reduced the wave equation to 2 first-order partial differential equations. Specifically, this first one here, which is partial of u with respect to t minus c partial of u with respect to x is equal to v. And I also have this one here, partial of v with respect to t plus c partial of v with respect to x equals 0. This is a decoupled system of partial differential equations. The strategy here is to solve the second one first for v because it doesn't involve u. Once I know v, I can plug it into the right side here and then get u, which is what ultimately we are interested in. U is the solution to the wave equation. All right. So the way we solve a first-order PDE is obviously much simpler than the wave equation, but for those that don't quite know, I'm going to do a very quick summary of the method of characteristics. So v is a function of two variables, x and t. We know from calculus 3 that the differential of v is the partial of v with respect to x dx and plus partial of v with respect to t dt. Now, if I divide both sides by dt, I get the fundamental relationship between the total derivative and of v and its partial derivative. So this is going to be partial of v with respect to x dx dt plus partial of v with respect to t. So if you compare this left side here with this here, dv dt is the same, and dx dt is going to be c. So along the curves in the tx plane that satisfy dx dt equals c, this left side here becomes dv dt. So this, for shorter PDE, simplifies to dv dt equals 0 along these curves, the family of curves in the xt plane given by this differential equation. I can solve for this family of curves by just integrating both sides with respect to t. I get x equals ct plus a constant. I'm going to call it g. This is the Greek letter. It's a characteristic coordinate that's used to indicate a certain member of the family. It is a constant along these curves in the xt plane. So I can solve for it. Xi equals x minus ct. Now, I can solve for v by integrating both sides with respect to t. It's going to be v. It's going to be a function of xi and t. This is equal to some arbitrary function f of the characteristic coordinate. Now, the reason I use the characteristic coordinate is because that's what the PDE is constant on along the curves in the tx plane. So now that I know what v is, I can change back to the original variables, x and t. So v as a function of x and t is f of x minus t, ct. And as I said before, now that we know what v is, we can plug it back into this first PDE here and get u. So the first PDE, that's going to be minus. Okay. So different color here. So this is going to be partial of u, partial of t, minus c du dx equals f, x minus ct. So we're going to use the method of characteristics again. So along the curves in the tx plane that satisfy dx dt equals negative c, this partial differential equation, the left side of it reduces to du dt equals f x minus ct. All right, so as before, we're going to solve the this differential equation here by integrating both sides with respect to t. I get x equals negative ct plus nu. This is another characteristic coordinate, the one for this PDE that we're solving right now. So I'm going to solve for that. I get nu equals x plus ct. So this differential equation here, it's a total derivative with respect to time, t. But I have x here. So what I have to do is write that in terms of the constant. So I'm going to plug in negative ct plus... Oh, I'm sorry, I call it nu. This is actually eta. My bad. Okay, so if I plug in this for x, this becomes du dt equals f. So negative CT minus CT, that's negative 2 CT plus eta. So eta is a constant along these curves in the tx plane. So so now this is in fact an ordinary differential equation. So to solve for u, I am going to integrate both sides with respect to time. So I get integral t, and I'm going to use r for my integration variable. So this is going to be f negative 2cr plus eta dr, and now plus another arbitrary function g of the new characteristic coordinate eta. All right, so to integrate this arbitrary function, I'm going to make a substitution. I'm going to say let w equals negative 2cr plus eta. So dw equals negative 2c dr. And that means that dr equals dw over negative 2c. So if I plug that in to the integral, I get, oh yeah, so I also have to take into account this integration variable t here. So if I plug that into here, it becomes negative 2ct plus eta, and then f of w, and then dr is dw over negative 2c plus g eta. I'm going to bring the negative 2c out in front because it's just a constant, so this is equal to negative 1 over 2c, and now integral negative 2ct plus eta. Sorry, my writing is getting kind of sloppy here. fw dw plus g eta. Now, f is an arbitrary function. The integral of an arbitrary function is another arbitrary function. I'm going to call that capital F, minus 1 over 2c, capital F of w evaluated at negative 2ct plus eta, plus g eta. This is 1 over 2, negative 1 over 2c, f, negative 2ct plus eta, plus g eta. And now, oh, I'm sorry, we're not quite done yet. So capital F is another arbitrary function, and negative 1 over 2c times an arbitrary function is another arbitrary function. So I'm going to call it, let's say, h. Plus g eta. So this is u of eta t. Now that I know what u is, I'm going to change back to the original variables, x and t. Now, negative 2ct plus eta, where is it? Here it is. So eta is x plus ct. So I'm going to plug that in here. So let me use a different color here. U x t equals h negative 2ct plus x plus ct. That's what it was, right? Yes. Plus g x plus ct. So u of xt equals h x minus ct plus g x plus ct. So this is the general solution to the one-dimensional wave equation. Physically, this represents the sum of two waves. one that travels to the right at speed c, that would be this term here, and a wave that travels to the left at speed c. We can determine these arbitrary functions if two initial conditions are provided to us. There are two because this PDE is second order in time. We can do that in a follow-up video, so stay tuned for that.